Hello everyone, my name is Avinash and I am a city planning student at IIT Kharagpur. In this video, I will talk about Ensemble Learning. Ensemble Learning is a machine learning technique that involves combining the predictions of multiple models to improve the overall performance of a model. Ensemble Learning is a supervised learning algorithm. The idea behind ensemble learning is that combining the predictions of multiple models will produce a more accurate and robust prediction than any individual model alone. Ensemble learning has become an important technique in machine learning because it can help improve the accuracy and reliability of predictions, which is essential for many real-world applications. How does ensemble learning work? Say we want to develop a machine learning model that predicts inventory stock orders for your company based on historical data you have gathered from previous years. We train 4 machine learning models using different algorithms: linear regression, support vector machine, a regression decision tree, and a KNN. But even after much tweaking and configuration, none of them achieves your desired 95% prediction accuracy. These machine learning models are called weak learners because they fail to converge to the desired level, but weak doesn't mean useless. You can combine them into an ensemble. For each new prediction, you run your input data through all 4 models and then compute the average of the results. When examining the new result, you see that the aggregate results provide 96% accuracy, which is more than acceptable. The reason ensemble learning is efficient is that your machine learning models work differently. Each model might perform well on some data and less accurately on others. When you combine all of them, they cancel out each other's weaknesses. We can apply ensemble methods to both predictions problems and classification problems, types of ensemble learning algorithms. There are 3 main types of ensemble learning algorithms: bagging, boosting, and stacking. Bagging, bootstrap aggregating. The bagging ensemble technique is the acronym for bootstrap aggregating and is one of the earliest ensemble methods proposed. For this method, subsamples from a dataset are created and they are called bootstrap sampling. To put it simply, random subsets of a dataset are created using replacement, meaning that the same data point may be present in several subsets. These subsets are now treated as independent datasets on which several machine learning models will be fit. During test time, the predictions from all such models trained on different subsets of the same data are accounted for. There is an aggregation mechanism used to compute the final prediction like averaging, weighted averaging, etc. In the bagging mechanism, a parallel stream of processing occurs. The main aim of the bagging method is to reduce variance in the ensemble predictions. Boosting. The boosting ensemble mechanism works in a way markedly different from the bagging mechanism. Here, instead of parallel processing of data, sequential processing of the dataset occurs. The first classifier is fed with the entire dataset, and the predictions are analyzed. The instances where classifier 1 fails to produce correct predictions, that are samples near the decision boundary of the feature space, are fed to the second classifier. This is done so that classifier 2 can specifically focus on the problematic areas of feature space and learn an appropriate decision boundary. Similarly, further steps of the same idea are employed, and then the ensemble of all these previous classifiers is computed to make the final prediction on the test data. The main aim of the boosting method is to reduce bias in the ensemble decision. Thus, the classifiers chosen for the ensemble usually need to have low variance and high bias, that is, simpler models with less trainable parameters. Stacking. The stacking ensemble method also involves creating bootstrapped data subsets, like the bagging ensemble mechanism for training multiple models. However, here, the outputs of all such models are used as an input to another classifier called meta-classifier, which finally predicts the samples. The intuition behind using two layers of classifiers is to determine whether the training data have been appropriately learned. Benefits of ensemble learning algorithms: improved accuracy. Ensemble learning algorithms can help improve the accuracy of machine learning models. By combining the predictions of multiple models, ensemble learning algorithms can mitigate the weaknesses of individual models and improve overall performance, robustness. Ensemble learning algorithms can also increase the robustness of machine learning models. By creating multiple models, ensemble learning algorithms can ensure that the final prediction is less sensitive to changes in the data or the model parameters. This can make the model more reliable and less prone to overfitting or underfitting. Diversity. Ensemble learning algorithms can also increase the diversity of machine learning models. By using different subsets of the data or different algorithms, ensemble learning algorithms can ensure that the individual models are diverse and complementary. This can make the model more flexible and better able to handle different types of data or tasks. Generalization. Ensemble learning algorithms can also improve the generalization of machine learning models. By creating multiple models, ensemble learning algorithms can ensure that the final prediction is not biased towards any particular algorithm or subset of the data. This can make the model more generalizable and better able to handle new, unseen data. Challenges of ensemble learning algorithms. Complexity. Ensemble learning algorithms can be more complex than individual models and can require more computational resources and time to train and deploy. This can make them less practical for some applications, especially those with limited resources or real-time requirements. Overfitting. Ensemble learning algorithms can also be prone to overfitting, especially if the individual models are too similar or the data is too homogeneous. This can lead to a model that performs well on the training data but poorly on new, unseen data. Bias. Ensemble learning algorithms can also be prone to bias, especially if the individual models are biased or the data is imbalanced. This can lead to a model that performs well on some subsets of the data but poorly on others, or that perpetuates existing biases in the data. Besides above challenges, there are some other trade-offs also. Using ensemble means you must spend more time and resources on training your machine learning models. For instance, a random forest with 500 trees provides much better results than a single decision tree, but it also takes much more time to train. Running ensemble models can also become problematic if the algorithms you use require a lot of memory. Another problem with ensemble learning is explainability. While adding new models to an ensemble can improve its overall accuracy, it makes it harder to investigate the decisions made by the AI algorithm. A single machine learning models, such as decision tree, is easy to trace. But when you have hundreds of models contributing to an output, it is much more difficult to make sense of the logic behind each decision. Ensemble learning can be applied to many different fields, including urban planning. Urban planning is the process of designing and managing the physical and social infrastructure of cities, towns, and other urban areas. Urban planners use a wide range of tools and techniques to make decisions about land use, transportation, housing, public services, and other aspects of urban life. Machine learning, and specifically ensemble learning, can help urban planners to make more accurate and data-driven decisions. One example of ensemble learning in urban planning is predicting urban growth patterns. Urban planners need to be able to predict where and how much urban growth will occur in the future in order to make decisions about land use, transportation, and infrastructure development. Ensemble learning algorithms can be used to create models that predict urban growth patterns based on a wide range of factors, such as population growth, economic development, and land use policies. Example of ensemble learning in urban planning: a team of researchers from China used an ensemble learning algorithm called AdaBoost to predict urban growth patterns in the city of Wuhan. They collected data on a variety of factors that were known to influence urban growth, including population density, distance to transportation infrastructure, land use policies, and economic development. They then trained an AdaBoost model to predict urban growth patterns based on this data. The AdaBoost model was able to accurately predict urban growth patterns in Wuhan over a 10-year period, with an overall accuracy rate of 83%. The researchers found that the model was able to capture the complex relationships between different factors that influenced urban growth, and that it was able to make predictions that were more accurate than those made using traditional statistical models. Example of ensemble learning in urban planning is optimizing transportation networks. Urban planners need to be able to design transportation networks that are efficient, safe, and sustainable. Ensemble learning algorithms can be used to create models that optimize transportation networks based on a wide range of factors, such as traffic patterns, air quality, and energy consumption. A team of researchers from the United States used an ensemble learning algorithm called Random Forest to optimize a public transportation network in the city of Atlanta. They collected data on a variety of factors that were known to influence transportation network performance, including traffic patterns, passenger demand, and environmental impacts. They then trained a random forest model to optimize the transportation network based on this data. Monitoring of physical characteristics of a target area without coming in physical contact, called remote sensing, is a difficult task since the data acquired by different sensors have varying resolutions, leading to incoherence in data distribution. Tasks like landslide detection and scene classification have also been accomplished with the help of ensemble learning. In conclusion, ensemble learning has many real-world applications in urban planning. It can be used to predict urban growth patterns, optimize transportation networks, and make many other data-driven decisions that are critical for urban planners. Ensemble learning can help urban planners to make more accurate, efficient, and sustainable decisions, and can ultimately lead to better quality of life for residents of urban areas. Thank you. Leave your thoughts in comment box.